Yeah, welcome all of you in this course, Electrical Technology. This is a course on electrical circuits, and I hope you will find this course not very difficult. And before I begin, I have a request to all of you. I often make mistakes, and if you find any mistake, please point out that to me immediately. That will be very helpful for me. Okay, so let's start. Let us start with a simple circuit with a battery and a resistor. So suppose we have a simple circuit with a battery and a resistor. Suppose this is 5 ohm, this is 10 volt. Then let me ask, how much will be this current I? What will be the answer? I will be
12.
10 volt by
Yes.
5 ohm, which is equal to 2 ampere. This comes from Ohm's law, right? And what does Ohm's law talk about? It talks about the property of resistors. What is that property? It says that suppose if we have a resistor and if current is flowing through it from say left to right, let that current be I, and if the voltage across it is V, more specifically if the potential of the left side of the resistor with respect to the right side is V, then V and I are related by this equation, V equal to IR. This is Ohm's law. Now the current through a resistor can have different values. The voltage will also take different values accordingly, but always voltage and current, they are related by this equation, where R is the resistance of this resistor. Now, therefore, the voltage and current relationship can be expressed pictorially using a graph where say x-axis denotes the current through a resistor and y-axis denotes the voltage across the resistor. Then V equal to IR is a straight line passing through the origin, and the slope of the straight line is the value of the resistance R. Okay, so that's the property of resistors. In this circuit, we also have a voltage source here. Now, what is the property of a voltage source? Of a voltage source, the property is as follows. The voltage across the source is fixed by the value of the source, by the specified value of the source. Okay. So if this is a 10 volt source plus minus 10 volt, and if the two terminals of this source are A and B, then VAB, okay, is always 10 volt. But how much is the current flowing through the source? Call this current I. How much is I? The current can vary depending on what is connected to the source. Okay. For example, if I connect say a 2 ohm resistance here, then this current will become 5 ampere if this is 2 ohm. However, for the same source, we saw when the resistance was 5 ohm, the current was 2 ampere. So current can vary, but the voltage is fixed. So this fact we can represent using a graph where x-axis is say current through the source and y-axis is the voltage across the source. Then the voltage is always constant. So we will get a horizontal line, straight line, and this is the characteristics of a voltage source. Okay. The current can also be negative. When can this current be negative? For example, say if I take the source 10 volt and connect this with another voltage source, stronger voltage source, say 20 volt in opposite direction, then the current through the 10 volt source will be negative. I mean the current I will be negative. Okay. So current can also be negative, but voltage is always constant. Okay. So this is therefore this type of sources are called voltage source because voltage is fixed but current is not fixed. Now, as you may guess, there is also something called a current source. Okay? And the symbol, circuit symbol of a current source is like this, an arrow within a circle. Okay? And the property is that the current through the source, this current I, is always fixed by the value of the source. Current through the source is fixed by the specified value of the source. Okay. Suppose I say that this is a 2 ampere source, then I will always be 2 ampere. But if these terminals are A and B, how much is the voltage VAB? The voltage can vary depending on what is connected across the source. Depending on what is connected to the source. Okay. So for example, if I take this 2 ampere source and if I connect say a 5 ohm resistance, then this current I will always be 2 ampere, no doubt, but this voltage, call this point A and B, then this voltage VAB from here to here with, I mean the voltage of the upper side with respect to the lower side will be 10 volt, 5 into 2, 10. But if I take the same source and if I connect say a different resistance, say if I connect a 3 ohm resistance, then this voltage will become 6 volt. So you may think that this current source is something which can automatically adjust the terminal voltage so as to keep the current constant. As you increase the value of the resistor, the terminal voltage will automatically increase to keep the current constant at 2 ampere. Okay? So therefore, now if I plot a graph representing the relation between the voltage and current for a current source, how will that look like? Anyone? Yes? That will be
Vertical.
a vertical line. Yes. So current is always constant, but voltage can vary. Okay. So this is the property of a current source. Okay. Now let me say take an example, small example. Okay. Suppose I have a current source 2 ampere and a voltage source say 10 volt and a resistor say 3 ohm connected together like this. The question is to solve this circuit. Okay, so basically you have to find how much is this current I. Okay, then say how much is the voltage across the resistor, how much is the voltage across say let me move it a bit, say this voltage across the current source, call that VI plus minus how much are these voltages and currents. V equal to how much, VI is how much, I is how much. Anyone?
2, 6 and 4.
Let's see. So the current I will definitely be equal to 2 ampere because the current source will definitely pass 2 ampere current through it. So I will be 2 ampere, and if so, then V, call this VR, voltage across the resistor. Okay, then VR will be 2 multiplied by 3, 6. So 2 ampere multiplied by 3 ohm, that is 6 volt. And how much will be VI?
4.
That you
Minus-
can find from using say Kirchhoff's voltage law. Okay, so call these points A, B, C, and D. Then the voltage from A to B, B to C is how much? That is VR, then plus 10 volt. Okay, so VR plus 10 volt. So it is 6 plus 10, 14 volt. Am I correct? Please check. Okay.
Sir, it should be minus 10 volt.
Sorry, this is, yeah, minus 10. Thank you. Minus 10. So this is, thanks a lot. So 6 minus 10 is minus 4 volt. Okay, with a minus. Okay, good. Very good. Let's take maybe another example. Okay, now say we have again a voltage source, current source, and a resistance. Now they are connected in parallel. The question is to find out the circuit solution if this is 10 volt source, if this is 4 ampere current source, and if this is 5 ohm. Okay, so let me call this VR plus minus, okay, from here to here. How much is VR? Okay, then if this current, this is I1, how much is I1, how much is I2, and how much is I3? Okay, what will be the solution? So first of all, VR is how much?
So 10.
It
10.
must be 10
10.
volt, definitely.
10.
And if VR is 10 volt, then I3 should be 10 volt by
2.
5 ohm, 2 ampere. Okay. Then how much should be I2? I2 should be
4 ampere. Minus 4.
minus 4.
Minus
Excellent.
Minus
Okay,
Four
because
in
it's in
reverse
opposite
side.
direction.
minus 4
So
ampere.
I2 is minus 4
Minus
ampere.
4.
And then how much is I1?
Minus 2 ampere.
Minus 2.
Minus
I1 will be
minus 2
I2
ampere.
plus I3. So that is minus 2 ampere. Excellent. Okay. Very good.
Sir,
I had one doubt.
Yes, please.
So in the last example, what if the current source does not have any resistance?
Current source is just current source. Current source is not resistance. So, okay, voltage source is voltage source. And
You have written Vi equal to minus 4.
see, this is actually a very common confusion which many people has is that V equal to IR, this relationship is valid only for resistors, is valid only for resistors. Okay, and it's not valid for anything else in general, voltage source, current source, and other things that we will study in the coming days. So please don't try to satisfy this relation V equal to IR for a current source or for a voltage source. Definitely it is not satisfied. So for example, for a current source, this is the relation for, between V and I. Of course, V and I are not proportional here. So V equal to IR is not true. Similarly, for a voltage source, V equal to IR is not true. V is constant, I can vary. Okay, so V equal to IR is only valid for resistors. Okay, but this is
Sir, what is then Vi there denote in the first example where?
in the first example here.
Yeah, what does Vi denote here?
VI is the voltage across the current source. Okay.
That
So that is the voltage from
what does
here
that-
to here.
so it means it does have some resistance, huh?
No, we do not talk about the resistance for this current source. We don't know what is there inside. We only know that the VI here, the value of VI can take different values, but the current through this source is constant, 2 ampere. That's all we can say about. We cannot write any relation between VI and 2 ampere. We cannot write that VI is 2 ampere multiplied by some constant. No, it's not
Got it, sir.
true. It's not true. Okay. Achha, fine. Now, next. So far I said that for a voltage source, the voltage must remain constant even if the current is varying. However, if we go to market and get, say, a battery, say a 1.5 volt battery for a radio or a transistor, most common one, 1.5 volt. Okay, so we may buy it, and suppose this is the plus, this is the minus side, and then we connect, say, a voltmeter across it. This is the symbol of a voltmeter which measures voltage, okay, plus minus side. Then the voltmeter is expected to give the reading 1.5 volt. Okay. But now at the same time, if I connect a variable resistor to the source, okay, say a rheostat, call this R, and R can vary, and as this R varies, then this current I will also change. Okay, this current and this current are same, I. So current will also change. And now if I keep varying this resistance, and for different values of resistance, if I measure the voltmeter reading, okay, so suppose I make a table, R versus I versus voltmeter reading, what we shall see is that as R decreases, then definitely I will increase, current will increase, but we shall see voltmeter reading decreases gradually. And if we make a graph, voltage versus current, so current versus voltage, we shall see a graph which is like this, which is not constant as we expect for ideal perfect voltage sources. Voltage is not constant, but it gradually decreases. Okay, why does that happen? Anyone?
Discharge of chemical in the battery.
So the reason
Discharge of
no, even if it is not discharging, discharging is one thing, but discharging will take some time. Over time, but even for even if you do this experiment for a short time, so that the discharge is not significant, you will still see for different values of current voltages going down as current increases. And the reason is
this
that
is the imperfection of voltmeter.
no, assume this is perfect
like
voltmeter.
real batteries, right?
Sir, internal resistance
Excellent.
of
That's,
the
yes.
Internal resistance of
So
battery.
absolutely right. So the reason is internal resistance. Okay. So what is that? As the current flows through the battery, it also flows through the electrodes, electrolytes, the chemical, everything, and they all have some resistance, and therefore there is some IR drop across that internal resistance. Okay, so we therefore model this battery as a combination of an ideal voltage source in series with a small internal resistance R. Okay, this is called this E the EMF of the battery. E here in this case is 1.5 volt. Although in this drawing I am showing these resistors separately from the source of EMF, but actually they are not separate. The resistance is distributed continuously throughout the battery, throughout the electrodes, electrolyte, etc. Okay, so but in circuit diagrams we model it or we represent it as a series combination of an ideal battery in series with an separate internal resistance. And now if say this voltage from here to here, okay, if I call A and B these terminals, okay, then this voltage from A to B, how much is V as a function of the current I? What can we write?
1.5 minus I R plus R.
Absolutely right. E, this E minus I into R, because the IR is the voltage drop across this small resistance R. Okay, so this is the relation between the terminal voltage, outside voltage, okay, and the EMF and the current that is flowing. Now, in this graph,
So why would it go down as a straight line?
pardon?
Why would it decrease like in a straight line?
If this equation is correct, if V equal to E minus IR is correct, then this is a straight line, right? With this point equal to E, and how much is the slope? Here
minus I.
Minus
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 r.
R.
Small r.
minus r.
Small r. It's minus
Minus
r.
r.
Excellent. Okay. So that's an equation of a straight line. Okay. So let me also ask. Therefore, so we see that the slope of this graph gives the internal resistance of a battery. Now, how much should be the internal resistance for an voltage source whose graph is horizontal, perfectly horizontal? Here, how much is internal resistance?
0.
Yes.
0.
Why is that so? Because the slope is equal to 0. Okay, let me put a minus. Since the slope is 0, so internal resistance here is 0. And this is called an ideal, that means perfect voltage source. And then this battery is called an practical voltage source, non-ideal, non-perfect. Okay, fine.
Sir, one question I had.
Yes, please.
Sir, the value of I is also dependent on V, right?
I is also dependent on, I depends, so I can also write I is equal to E divided by capital R plus little r, correct?
Yes, yes.
Okay, so if you change capital R is the variable, then capital I will change and capital V will change. Now, in a similar manner, we can also talk about a practical current source. You know that for an ideal current source, if this is the current I and this is voltage, then this current should remain constant irrespective of the terminal voltage. So this is the case for an ideal current source or a perfect current source, which we studied here earlier. This is ideal. But if we get a practical one, actual current source, okay, let me draw that here as a box, okay, and this is a practical current source. It has two terminals, and we can connect again a variable resistor or a rheostat. So if R increases, then the terminal voltage will also change, okay, and we can take an ammeter to measure the current that flows for different values of capital R, external resistance. And for a practical current source, we will see that as the voltage increases, current drops. This is the case for a practical source. It doesn't stay constant, it drops like this. Okay, now how can we explain this behavior, or how can we model this behavior that current decreases for a practical current source as terminal voltage increases? Okay, so here this is a practical current source. And V is the voltage from here to here, plus and minus. Okay, so how can we model this dropping behavior? Again, we can model it using internal resistance. We can say that this practical source is equivalent, similar to an ideal source in combination with some resistance. But if we now put this resistance like this in series, but then it will not be able to explain this dropping characteristic. Why? Because if I call this current source I naught, then how much will be this current I? It's always equal to I naught.
Irrespective of the series resistance, it will give the same current, right?
Right. So this cannot explain this behavior. Therefore, to explain this, we have to model this with a parallel resistance. Call it R. Okay. And now let us see what is the relation between this external current and I naught as a function of the voltage V. How much will be I? Before that, how much is this current here?
V by R.
This is excellent, V by R. And if this is V by R, then how much is this capital I?
I naught plus V by R.
I naught minus.
Minus
V by R.
Excellent. So I is I naught minus V by R. Okay. So again, this is a straight line relationship between capital I and capital V. Okay. And you may also draw this graph as follows, with y-axis as voltage and x-axis as current. Okay. Then how will the graph look like? Like this. As voltage increases, current decreases. Okay. And how much is the slope of this line?
Minus
1 by R.
minus
Minus 1 by R or R? It's the V by I, right?
Minus R.
Yeah. Okay.
oh yeah. Sir,
Yeah,
I had one
yeah.
question.
Just before that, kindly keep your cameras off. Some of you have your camera on. Please turn it off, otherwise that will get recorded in the video. Shivram Sharma, please keep it off. Anyway, I hope my screen is still visible to the other students.
Yes,
Yes.
sir.
Okay, so
Yes,
let me
sir.
continue. Yeah. Okay. So fine. Acha, then let me ask, how much is the internal resistance, therefore, for an ideal current source? Okay. So we saw before here, this is the graph for an ideal current source. Okay. So let me ask, how much is the internal resistance here?
Infinity.
Infinity.
Excellent.
Infinity.
Okay, so internal resistance for an ideal current source is infinite, and for an ideal voltage source, we already saw this. How much was this? 0.
Zero.
Zero.
Sir,
Yes, please.
sir, here I had one doubt. So like here I naught, like, do we assume it's a value or do we know what it is? Like I was confused. Like we assumed that the internal resistance for the battery, the internal resistance is in parallel to the voltage, means the voltage source. So I was confused. Like I naught, do we assume it's a current value that passes through the battery or what? Like I am confused a bit about
What
that.
is I? Acha, what is acha? One way of saying how much is I naught is you measure, I mean in this circuit, you measure the ammeter reading, okay, with,
Okay, sir.
I mean when this resistance is 0. That means voltage is 0, okay, because in this graph then you will see when voltage is 0, then this is equal to I naught, okay. So you may write I is equal to I naught when R is equal to 0, that is V equal to 0. So in that way you can find what should be the value of I naught.
Sir, also, sir, here V is the voltage across the terminals of the battery, right?
Please don't call this battery, because normally the term battery is more similar to a practical voltage source, but this is a current source. Don't call it battery, call it current source, practical current source.
Okay, so it's the means V is the voltage across the practical current source. Okay.
Yes,
Sir.
yeah. Okay, fine. Acha. Now, one thing please you observe, this is the graph, VI graph for a practical current source, which is a dropping straight line. And before this, we saw for a practical voltage source, the VI graph is also a dropping straight line. So in one way, you can see that they are somewhat similar. I mean, there is some similarity. Okay, now let us explore this similarity under a special situation. Okay, so suppose I have a practical voltage source battery whose EMF is E, internal resistance is call it R1, and let this to be the two terminals of this battery. Okay, let me put this in a box. And at the same time, consider a current source, practical current source, which is equivalent to an ideal current source in parallel with R2 parallel resistance. And let me again put this in a box. Let this be I naught. Okay, and suppose when R1 is equal to R2, so that we have two sources, one voltage source practical, one current source practical, but their internal resistances are same. And also E and I naught, they are related as E by I naught. Let me call this R1 equal to R2 equal to R, and E by R naught is equal to R. Under that situation, compare the two sources. Okay, compare these two different sources. If I call this voltage, external voltage, terminal voltage as V, and external current as I, of course there should be something connected here. Okay, some circuit must be there, otherwise I will be 0. So some circuit is there. And here, suppose this current is I and this voltage is V. And again, some circuit is here. what is the relation between capital V and capital I for the voltage source? Capital V is
V equals to
E minus IR.
E minus IR. Excellent. And what is the relation between V and I for the current source? So we can write I is equal to
I naught minus V by
I
R.
naught minus V by R. So from this we can write V is equal to I naught R minus IR. And since E by I naught is R here, we have chosen this relationship. So that means here we have V is equal to E minus IR. So you see, these two equations are exactly identical. What does this mean? This means that the VI graph for both these sources will be identical. VI graphs will be the same for the both the sources. Okay, what does this mean more? What does this tell? It also says that if this is terminal A and B, here also A and B, then if I connect, say, some resistance between A and B across this voltage source, and if I connect the same resistance between A and B for this current source, then the current through both the resistors will be same. The voltage across both the resistors will be same. Not only a resistance, if I connect any circuit between A and B, and if I connect the same circuit between A and B for the current source, then that circuit will not see any difference. Okay, so if the same circuit is connected between A and B, then the two circuits will not see any difference. Okay, so in this external circuit, nothing will change, no matter whether this external circuit is connected to this voltage source or to this current source. Therefore, we call these two sources as being equivalent.
Sir, means we can say the current source will behave as the voltage source only.
Yeah, the other way also you can say voltage source will behave as the current source.
Yeah, okay.
Okay, so
sir, basically we will get the same graph for both, and between the terminals A and B,
yes,
for both the circuits we will get the same effect if we join any device.
Yes, absolutely, absolutely, yes. Okay.
Okay, sir.
Yeah. So now maybe we take a small example, a small problem. Okay. Yeah, let me take this example. Okay. So we have a circuit, basically three voltage sources and with some series resistances. They are connected together in parallel like this, and let me call this voltage as VAB. I mean the voltage of terminal A with respect to terminal B. Okay, and here the question is VAB equal to how much? Okay, E1, E2, E3, they may be different. R1, R2, R3 may be different. how much is VAB. Okay, so let us solve this question using the idea of voltage source and current, practical voltage source and practical current source equivalence. Okay, so what we will do, let me make a copy of this circuit. Okay, so this is a copy of the circuit, and now let me remove this voltage source and this resistance, and in place of that let me put a current source and a parallel resistance like this, and I choose this resistance value to be same as R1, and I choose this current value to be E1 by R1. And if so, then you see that this part inside the circle and this part, they are equivalent. Okay? If they are equivalent, that means what? In the outside circuit, that means in the circuit outside the circle, nothing is changed. Inside the circle, of course, I have changed it, but outside nothing is changed. So therefore, the voltage VAB is also same as that in the original circuit. Okay, so this is equivalent to this. And then, if so, let me make another copy. And now what I will do, I will remove this second voltage source and the resistance and replace it with a current source and a parallel resistance. What should be the value of this resistance to keep it equivalent to the original one? It should be
R2.
R2. What should be this current source value?
E2 by R2.
E2 by R2.
E2 by R2.
Excellent. Now, this new circuit is still equivalent to the original circuit in the sense that the black color portion is unchanged. So voltage VAB is still unchanged. Now, in the same way, even if I change this third branch with a current source in parallel with a resistance, if this is R3 and if this current is E3 by R3, then still the black portion is not changed. So VAB is still the same. So this circuit is still equivalent. Okay, the sources are changed, but outside portion is still unchanged, and nothing will change there in the outside portion. So VAB is still remains same. Okay, and now this third circuit is much simpler to solve. What I will do, I will simply redraw the circuit by keeping the current sources together and the resistors together. Okay. Suppose this is this is R1, R2, R3. These currents are E1 by R1, E2 by R2, and this is E3 by R3. Okay, then still the voltage VAB is same. VAB will remain same. Now, can you find out how much is VAB in this finally modified circuit?
Yes, sir. E1 by R1 plus E2 by R2 plus E3 by R3 by 1 by R1 plus 1 by R2 plus 1 by R3.
Absolutely right. Okay, if I call this current I, okay, and then how much is I? I is equal to E1 by R1 plus E2 by R2 plus E3 by R3. This is capital I, and this capital I amount of current is flowing through through this parallel combination of these three resistances, R1 parallel, R2 parallel, R3. Okay, so this should be equal to the total voltage VAB, which is same as, if I simplify, E1 by R1 plus E2 by R2 plus E3 by R3. And how much is this parallel combination of the three resistances? It is 1 by R1 plus 1 by R2 plus 1 by R3. So that is the voltage VAB. Okay. Is it fine?
Yes, sir.
That's it. Okay.
Yes, sir.
Okay. Then this was a fairly simpler circuit. Now let us learn how to solve bit more complicated circuits. Okay. So for that, let me take this example. Okay, so we have a circuit, and this has 4 sources, 2 voltage sources, 2 current sources, and 4 resistances. Okay, the question is to solve the circuit. That means find out the value of the voltages and currents in and across all the branches everywhere. Okay. How? So we will learn several techniques for solving complicated, more difficult circuits. So the first method that we are going to learn is called superposition method or superposition principle. Okay. What I will do, I will make several copies of this original circuit. Okay. Copy and paste. Copy, paste, and okay, so let me make several copies. So this is the original. Okay, this is copy 1, copy 2, and this is copy 3. Okay, we can take more copies if required. Achha. Then what I will do, in the first copy of this circuit, you see there are 4 sources, 1, 2, 3, and 4. There are 4 sources. Now what I will do in this first copy, I will keep only the first source, this current source, and I will remove all other sources. Actually, I will replace all other sources by their internal resistances. Now, as we know, we have seen that internal resistance for ideal voltage source is 0. So let me replace this voltage source with 0 resistance. Similarly, this voltage source I will also replace with 0 resistance. And this is a current source. Current sources have infinite resistance. So let me replace with infinite resistance or open circuit. Okay. So what I am doing, keeping one source and replacing other sources with their internal resistance. That means 0 for voltage sources and infinite for current sources. Okay, so in the first copy of this circuit only one source is present. Similarly, in the second copy of this circuit, let me keep say only this source, 6 ampere source, and replace all other sources with their internal resistance. So this 4 ampere source is replaced by infinite internal resistance, 10 volt, and these 12 volt voltage sources are replaced by 0 resistances. Okay, so only one source is present. And then in the third copy, let me remove this 4 ampere source and replace it with infinite resistance, removing a 6 ampere source and replacing it with infinite resistance, and let me keep these two voltage sources. Okay, so so in this way you see that I have 3 copies and all sources are kept exactly once. They are kept in exactly one circuit, and in all other circuits they are replaced by their internal resistances. So keep all sources or use all sources exactly once. So use all sources exactly once, not more than once, not less than once. So you see, this current source is present once, this current source is also present once, these 2 voltage sources are also present once, although together, no problem. Now, we will solve these 4 copies of this circuit separately. Okay, solve this circuit separately. So what will be the solution for the first copy? Okay, how much will be this current here? This one, anyone? Okay, if I call this, let me call.
4 by 3.
A, B,
And 4 by 3.
C, D, etc. So at node C, we can apply current divider rule. Okay, so you have 2 paths. One has 3 ohm resistance, another has 7 ohm resistance. Okay, so if you apply current divider rule, I hope you know. If not, you may ask me, no problem. So then this current is total current 4 ampere multiplied by the resistance of the other path, which is 7, divided by the total resistance of the 2 paths, which is 10. Okay, so therefore this is, how much is this current? 2.8. Okay, so that means this current is also 2.8. Okay, then how much will be this current here through 5 ohm resistance?
1.2. This
must be 1.2. Okay, and this current is also 1.2 ampere. Okay, in a similar way, let us now solve this copy 2. Okay, how to solve? You can apply current divider rule at node D. So how much will be this current? Right side current, that will be 6 into 6 by 10.
6.
Okay, that is 3.6 ampere. Please check. Okay, otherwise I will be in trouble. I often make mistakes. That's my problem. So please check. Okay, and then if this is 3.6, then this is also 3.6 ampere. and then this current, left side current will be 2.4, and then this is also 2.4 ampere. Okay. Then let us solve copy number 3. Okay. So basically, two sources, 10 volt and 12 volt, they are connected together, so they are equivalent to 12 minus 10, 2 volt source, one single source 2 volt. Okay. And how much will be the current?
2.2.
This current will be 2 volt divided by 2 to 4, 10 ohm, so that's 0.2.
0.2.
0.2 ampere. So this is also 0.2, and the left side current therefore will be, so this is in series, so this is also 0.2, this is also 0.2 ampere. Now what we will do, we will add the solutions of these 3 copies together to get the solution of the original circuit. Okay. So for example, consider this 5 ohm branch in the original circuit. How much will be the current? So here we have 1.2 from right to left, then 2.4 from left to right. Okay, so that means, and here 0.2 from right to left. So if you add these 3, 2.4,
1 ampere.
1 ampere from left to right.
1 ampere, absolutely right. 1 ampere from left to right. Okay. Similarly, between B and C, okay, that means through 2 ohm resistance, the current will be 4.8,
5 ampere.
5 ampere. Okay, and then through this 1 ohm resistance, 2.8, 2.4, that means 3.2, 5.2, 5.2, 5
ampere.
Absolutely right, 5 ampere. Yeah, and therefore, and if this current will be how much?
1 ampere.
1 ampere.
1 ampere? Okay, I'm not doing it. I'm trusting you. Okay. So this will be the solution of the original circuit. This is called superposition method or superposition principle. Okay, fine?
Sir?
Yes.
Sir?
Yes.
So may I ask one question?
Yes,
like
please.
for the copy 3, we have kept 2 sources together.
Yes.
So
yes.
we can make also one copy 4 where like means
Yes,
in
yes,
copy
yes,
3 we
yes,
can
yes,
take
yes,
one
yes.
source and in
That is
copy
also
4
possible.
another.
Yeah. You can make also 4 copies and keep these 10 volt and 12 volt sources in separate copies. Yeah, that is also possible. Just make sure that
it is according to the calculation, like which will simplify the calculation we will do.
Absolutely right. Only thing you need to make sure that all sources are used exactly once, not more than once, not less than once. Okay. Yeah, fine. Now, so that was one method for solving difficult circuits. Let us learn one more method. Okay. Let me take the same circuit, same question. Let me remove the solution. Let's pretend that we don't know the solution, and the method that we are going to learn is called nodal method or nodal analysis. Okay, so notice that this circuit has 1, 2, 3, 4 junctions. Let me call them A, B, C, and D. Okay, so it has 4 junctions. So we will assume unknown junction potentials or node potentials. Assume unknown node voltages. Okay, for example, here VA, here VB, VC, VD, etc. Now, one thing you can do, we can choose any one node to have zero potential. That means we call that as the reference node. Okay, for example, I can choose VD to be equal to 0. Okay, so let's assume that this point is at the ground potential. Okay. Now we have three unknown potentials, VA, VB, and VC. We will solve this, these three unknowns using mainly Kirchhoff's current law. Okay, so next, apply Kirchhoff's current law at each node. Okay, so let me start with node A. So let me apply KCL at node A. Okay, so let me find out the total current going out from node A is how much. Okay, so first let me call this current I1, this as I2. Okay, then how much is I1? I1 is, this point is at VA and this point is at 10 volt.
10.
So
VA minus
I1
10
is
upon 1.
VA minus 10 divided by 1. This is going out. Then how much is I2? I2 is VA minus VB by 5. This is also going out. And then through this upper path, 4 ampere current is going out. Okay, so this is the total.
Sir, if we consider it going out, then we should, yes.
Okay, fine. Achha. So this is what we should have. Now, if you simplify this equation, you will get, please check, I think 6 VA, 1 VB, and then we will have right 30. Please check. Call this equation number
Yes,
1. Okay. Now similarly, let's apply KCL at node B. Okay. So total outgoing current is how much? You can also calculate total incoming current. That should also be equal to 0. So we see that 6 ampere current is going outwards, downwards, okay, and then minus I2 going to the left, and if this current is I3, okay, how much is I3? I3 is VB minus VC by 2. This is also going out, and let me put the value of I2. I2 is VA minus VB by 5. So the total should be equal to 0. If you simplify, plus 5 VC. This should be equal to 60. Okay, please check this if I am correct. This is another equation. Okay, and so similarly at node C, what will be the equation? Can someone dictate me, please? So first, the downwards current is how much? Vc minus 12 by 2 downwards. Then the current going upwards is how much?
Minus
4. Minus
And
4.
yes, and the current going to the
Minus
left
I3.
is
VC minus
VC
VB by 2.
minus
Plus
VB by 2. The total should be equal to 0, and this 2 VC minus VP equal to 20. Please check. Okay.
Sir, and the first one, shouldn't it be equal to minus 10?
In equation 1,
Yeah,
right side should be 10.
minus 10.
It should be
Minus
30.
10.
It should be 30, sir.
Okay,
No, sir,
so
it will be 30.
you I
That's
mean,
a left
anyway,
side.
so this simple thing you can, I mean, you don't, please don't trust on me about these simplifications. Okay, so I may
Okay,
make mistakes.
got it,
Uh,
got it, got
yeah.
it, got it, got it. Never mind, sir.
But I mean, just follow the overall method. Don't rely on finer simplifications on me. I am always very prone to mistakes. Okay, yeah, so now we have 3 equations and 3 unknowns. So can you solve it yourself? Or do I have to do
Yes,
it?
sir.
Yes, sir.
Yes,
So,
sir.
so solving is your homework. Homework. Solve the 3 equations. Okay, and anyway, we know the solution because we already did it with a different method, so you can check. Okay, now once you know VA, VB and VC, then you can calculate all the currents. Okay, for example, once you know VA, I1 will be that value of VA minus 10 by 1 ohm. So once you solve these 3 unknowns, you can calculate all other desired quantities, desired voltages, desired currents, everything. Okay, so that is another method. Okay, next let me take one more example. I will take this question which we already solved. Okay, now the task is to find out VAB using nodal method. Okay, so in this circuit, we see we have 2 junctions, 2 nodes, A and B, only 2. Okay, and any one of that you can assume to be at 0 potential. Let me assume VB at 0 potential reference point, and then this is at VA. So VAB will be definitely equal to VA. So let us find out how much is VA. How do we do? So let us apply KCL, Kirchhoff's current law, at node A. Okay, let me call these currents as I1. This current is I2 and this current is I3. Okay. Let me write I1 here. Okay, so we should have I1 plus I2 plus I3. This is the total amount of current entering node A, so that should also be equal to 0. Now how much is I1?
VA minus
E1 by R1.
E1 by
Yes.
R.
Oh,
So this is I1.
okay,
Okay.
okay, okay.
Similarly, VA minus E2 by R2 is I2 and VA minus E3 by R3, this is I3. Together they add up to 0. So now if you simplify, you will get VA common 1 by R1 plus 1 by R2 plus 1 by R3. Right side will be E1 by R1 plus E2 by R2 plus E3 by R3. So you will get how much is VA from here. And this gives the same result as we got earlier using voltage, equivalence between practical voltage and current source. So this verifies our calculation. Okay, fine.
Sir.
Yes.
I have one doubt. Like,
Yes.
will it be E1 minus VA or VA minus E1? Like,
Okay, so you can do it in this way. So this point is at VA, okay, and therefore this point between just below the voltage source is at
yes, sir. Yes, sir. It is
minus
VA minus E1
E1.
and it is 0 divided by R1.
Okay, so yeah.
I got it.
Yeah,
In this point, it is 0
At this point is 0. Yes.
divided by R1.
Yeah.
Okay, sir.
Okay, fine. Now let me just take a very specific case.
In that direction, from VA minus E1 to 0 means
Not actually, that depends on the value of VA minus E1. Like we can assume it in a certain direction, but that will be adjusted on the given on the value of VA minus E1.
Could you please repeat the question? Is there any question or is it solved? Hello, do you have a question or have you already solved it? Okay, I assume it's solved, so let me proceed. Now, okay, let me take a very particular example. Here I will give you the values of this, exact values of these sources. 50 volt, 40 volt, and say 60 volt. And these resistances are 10, 20 ohm and 20 ohm. Okay, so how much will be VAB? You can use this previous result. So that will be 50 by 10 plus 40 by 20 plus 60 by 20 by, just a second, 1 by 10 plus 1 by 20 plus 1 by 20, 50. Okay, 50 volt. Thank you. But now let us learn one more method for solving circuits. Okay, and this method is called mesh or loop analysis. Okay. So what we will do, let us forget this solution. Let us assume that we don't know this, and we will solve this using a new method. In this case, you see that this circuit has two loops. One loop is this is one closed circuit, and this is another closed path. Okay, if I call this A, B, C, A is already used. Okay, let me remove this. Okay, A, B, C, D, E, F. Then we have a loop or a mesh which starts from A, then goes through B, then E, then F, back to A. This is one loop. Then you can also consider this another loop starting from B, go to C, D, E, and back to B. Okay. So to solve this circuit, we will use Kirchhoff's voltage law, KVL, applied across these loops. Okay. So let's apply KVL on the loop AB, EFA, and let us find the total voltage drop or total voltage rise. Okay, total voltage rise. Okay, so A to B there is no voltage rise or drop. Then B to E there is a 40 volt drop, so minus 40. Okay, this is a voltage drop, and then through this 20 ohm resistance, how much current is flowing? If I call this current as this current loop current IL1 and this current as IL2, okay, so we are assuming that two currents IL1 and IL2, they are flowing along these two closed paths, two closed loops, and therefore the current through this 20 ohm resistance is sum of IL1 and IL2. So IL1 going downwards and IL2 going upwards. So this is the current, total current going downwards. So multiplied by 20 ohm, this is a voltage drop. Then from F to A, we have a 10 ohm multiplied by IL1, this amount of voltage drop. Okay, and then there is a voltage rise plus 50 volt. This should be equal to 0. Did you follow how I did this? Any question here?
No, sir.
No, sir.
Okay, so if you simplify this equation, what will you get? Minus 30 IL1 plus 20 IL2 will be equal to minus 10, implying 3 IL1 minus 2 IL2 equal to 1. Okay, so this is one equation. Okay, and yeah. Now, similarly, let us find the total voltage rise in this loop B, C, D, E, B. Okay, starting from B, so we have first So C to D minus 60 volt drop, then minus 20 ohm into IL2. This is again a voltage drop. Then E to B, first we have a 20 ohm resistance, and IL2 minus IL1, this much current is going upwards, so this is a voltage drop, and then a voltage rise of 40 volt. Okay, total should be equal to 0. So we are using KVL and we are calculating total voltage rise. You can also calculate total voltage drop. You will get same thing. And this, if you simplify, you will get minus 40 IL2 plus 20 IL1 minus 20 equal to 0, implying IL1 minus 2 IL2 equal to 1. So this is another equation. Okay, so we have two equations, but the values of IL1 and IL2, these are unknowns. So we have two unknowns and we have two equations, so we can solve for IL1 and IL2. How do we solve? Okay, so if I subtract equation
IL1 equal to 0.
Let
IL2 equal to minus 0.5.
If we just subtract these two, we will get 2 IL1, then IL2 cancels, and right side is 0, so that means IL1 is equal to 0. And once you know the value of IL1, you put the value in any equation, and you will get IL2 equal to minus 0.5. Am I correct? Yes, I guess. Okay, so
Yes.
therefore the solution is as follows. Okay, so we started by assuming two unknown loop currents. Okay, and now we know that IL1 is 0 ampere, and this is minus 0.5. That means actually in the opposite direction we have plus 0.5 ampere. Okay, so this is the circuit solution, and now you can find any other currents or any other voltages. So suppose if I call this I1, I2 and this I3, then how much is I1? I1 is same as IL1, 0. How much is I2?
I2 minus 0.5.
So that
Minus
is
0.5.
0 plus minus, so plus 0.5. So that is 0.5 ampere. And then I
I2 will be minus 0.5.
I took, yeah, thank you, minus, right? And I3 is 0.5 plus.
Plus 0.
Okay, and then you can calculate how much is V, capital V. So that will be 60 volt minus 20 ohm into 0.5 ampere. So 60 minus 10, 50 volt. Same as what we got earlier. Okay. Fine. Yeah, here in these equations I have omitted the units, volts, amperes, etc. Because all are assumed to be in SI unit. Yeah. Okay. Fine. Any questions so far? Anyone? Any question?
Sir, will you upload these pages?
Yes, yes. Any question regarding the topic? Please repeat.
Hello, sir.
Please repeat.
Which method do you prefer to use?
That's basically an art to decide which method is easier for a particular problem. Okay, that's an art that you have to develop, and there is no general guideline in general. Okay. For some problems, some methods will be easier to use, some methods will be more complicated to use. Okay, so today, let me see what have we done. Okay, any questions so far? No question? So we have learned 3 methods: mesh method, nodal analysis, and superposition principle for solving general circuits. Okay, so let me ask some more question. This problem we have solved earlier today. Okay. Now, let me ask, how much is the power supplied by the voltage source? Okay. How much is that? That will be 10 volt into I1.
20 volt.
So 20 watt is the
20 watt. 20 watt.
It will be 10 volt into I1, and I1 is -2. Okay, so it will be minus 20 watt. Minus 20 watt supplied, that means it is consuming plus 20 watt power. Okay, so when I say power supplied, I implicitly mean electrical power supplied. Okay, and actually, powers cannot be generated or consumed in an absolute sense. It can be only converted from one form to the other form. So here, when I say electrical power supplied or generated, that means some other forms of power, maybe chemical power, maybe mechanical power, is converted into electrical power. Okay, so be careful about the signs. So in this case, power is actually consumed by the voltage source. Electrical power is consumed.
It's charging or discharging? Sir? Charging only, right?
If it is a chargeable battery, then it may get charged. If it is a normal battery, then it will just be converted into heat. If it is a generator in a power, like a power plant, then it may get converted into mechanical power. Okay, so that we don't know, but what we can definitely say that electrical power is consumed and electrical power is gone, converted into some other form in this voltage source. Then say how much is the electrical power supplied or generated by the current source. How much is this voltage from here to here?
40 volts.
This is 10 volt. Okay, so plus minus. So this will be 10 volt into 4 ampere, that is 40 watt. Okay, you see here, the source is pushing positive charge from a lower potential to a higher potential. That means it is doing some work, and that work is converted into electrical energy, maybe electrostatic energy. So electrical energy is generated. Okay. In the same way, in a similar way, for this voltage source, actually the current is flowing down 2 ampere from higher to lower potential. So that means it is not doing any work. Work is being done on its own by the electrostatic energy. So this is not generating any electrical power, it is consuming power, this voltage source. Okay. And finally, how much is the energy or power generated, not generated, consumed, say, consumed by the resistor. Okay, I3
20 watt.
Is
I3 square
20 watt.
I3 is how much? 2 ampere is flowing from positive to negative side, 10 volt. Okay, so that means energy is consumed. Okay, positive charge is flowing down flowing down the I mean the what should I say, electrostatic potential gradient. So therefore power is consumed. This is 20 watt. Okay.
20 watt.
So now let us see whether energy balance is satisfied. So voltage source is consuming 20 watt, resistor is consuming 20 watt, and current source is delivering, generating 40 watt. So altogether it's balanced. Okay. Fine. Any questions so far?
No, sir.
Okay, so then maybe we Acha, let me just ask, am I going too fast? Anyone having any problem with my pace? I will try to adjust it.
No, sir.
No, sir. No, sir.
Okay, fine.
It's okay.
Because anyway, this semester we have a very few number of classes available, and the syllabus is quite significant. So, okay. So let me ask a simple question. So here we have a current source, and the task is to solve this circuit. Okay, so suppose this is 2 ohm, 3 ohm, 5 ohm, okay, say 3 ohm, and maybe 2.5 ohm. Okay, and suppose this is 2 ampere current source. Solve this circuit. You can use any method you like, nodal, mesh, keep. But this will be a homework for you to solve this question using Nodal method or mesh method and get the solution. Find out all the currents, say I1, I2, I3, I4, I5, find out all the currents. Okay, but I will give you a simpler technique which you can apply in this question and sometimes in many other questions. So that is called star delta equivalence. What is it? Let me first talk about it. Okay, so suppose you have three resistances. Let me call them as let me call these nodes as A, B, C, and let me call this R A, R B, and R C. And this is one circuit, and another circuit has three resistances connected in a different way. Let me call these nodes as A, B, and C. This is RAB, RBC, and RCA. Now both this circuit has three terminals, okay, A, B, and C, and you can connect other circuit elements, voltage source, current source, resistors, etc., complicated circuits between these three nodes A, B, and C in either of these two circuits. Call this circuit 1 and call this circuit 2. Okay, let me call this actually circuit Y or star because this looks like a star, and let me call this circuit delta because this looks like the Greek alphabet delta. Now there is a rule. The rule says if RA, RB, and RC, these three resistances, are related to RAB, BC, CA by certain equations which are like this. RA is equal to RAB into RCA divided by RAB plus RBC plus RCA. Okay, so you see RA is the resistance connected to node A, which I am writing as equal to, in the other circuit, the product of the two resistances RAB and RCA, which are connected to node A, divided by the sum of the three resistances. Okay, if this is the case, if, and also if RB is equal to, in a similar manner, in a symmetric manner, this is RBC multiplied by RCA divided by RAB plus BC plus RCA. And can you guess What am I going to write? RC. Sorry, I have
RCA.
made ABBC.
Sir, in
RCA, RBC by RA.
I have made
RBC
could be
into
AB.
I have made a mistake
R-
here. R A B B C. Yes. What should be RCA in a symmetric manner? R C A.
RBC into RCA
Right.
by RAB plus RBC plus RCA.
Basically, the product of the two adjacent resistances divided by the sum of the three resistances. If these equations are true, then the above two circuits are equivalent. What do I mean by the two circuits being equivalent? I mean that, okay, suppose if you connect
We can
a
replace
circuit
one circuit
here,
with another.
call it circuit 1 between A and B, okay, some circuit here, circuit 1 I connect here, the same circuit I connect here, circuit 1, okay, here I connect some other circuit, circuit 2 between A and B, and the same circuit I will put on the right side as well. Okay, and you can connect also something here. Here also you have to connect the same thing, circuit 3. Then the circuit 1, 2 and 3, they will not see any difference, any change. Okay, whatever current is flowing here, if it is I1, here also the same current I1 will flow. If the voltage from here to here is V2, then the voltage from here to here will also be V2. Okay. So the outside circuits, external circuits, will not be able to see any difference. They will not know whether they are connected to this star circuit or they are actually connected to delta circuit. So in the outside world, external world, no difference can be perceived, can be seen. If the three resistances are satisfying these equations. This is the rule. I am not going to prove this rule, okay, because we have a shortage of time, but let me use this rule to solve this question. Okay, so what I will do, I will draw the equivalent circuit. So I'm first making a copy. Now consider this left side delta. You see three resistances connected like a delta, and so let me replace these three with the equivalent star configuration. So we will have 1, 2 and 3. Oh, this is also gone. This is also removed. Okay. Now, please note down this formula. Okay. Please note down these formulas. Okay. Basically, the product of adjacent resistances divided by the sum of 3. Okay. From this, can you tell me what should be the value of this resistance so that these two circuits are equivalent?
0.6.
3 into 2, so this is 3 into 2 divided by 3 plus 2 plus 5, okay, 10. So this is 0.6, 0.6 ohm. Similarly, how much will be this resistance?
1.
2 into 5, 10 by 10, 1 ohm. And this one will be 3 into 5, 15 by 10, so 1.5 ohm. Now this circuit is similar, is equivalent to the original circuit in the sense that currents in the black portion will not change. The gray portion is of course changed, but the outside part, black region is not changed. So this current I2 will remain as this current I2, and this will also remain I4 as the original I4. Can you find out how much will be the value of I2 here? So you see 2 ampere is coming here, and then at this star point you can apply current divider rule. Okay, so how much will be I2? Total current,
Sir,
2
1 ampere.
2 ampere multiplied. So we have two paths. This path has resistance 4 ohm. This also has, so both the paths has same resistances. So 4 ohm divided by 4 plus 4 ohm. So that means 1 ampere. I2 is 1 ampere. So therefore I4 will also be 1 ampere. Okay, now next, how much is I1? So we got I2, we got I4. How much is I1? Will this I1 be same as this current here? Will this be I1? Anyone? Is this also I1? Is
No,
this
sir.
current I1?
No, sir.
No, because this part is changed. So this part is not same as the original circuit. Okay, so how to find I1? We can do some kind of back calc. So I2 we already know this is 1 ampere. I4 is 1 ampere. Okay, now so I2 and I4 are 1 ampere. Now if I choose this as the reference node, 0 volt, okay, then what should be the potential here? At call this node node A. At node A, how much should be the voltage? It should be
3
1
volt.
ampere, so 3 volt. So this is 3 volt. Okay, and then what is the voltage here? This is
2.5.
2.5 volt. So then how much is I5? I5 is 0.5, so 0.1 ampere. Okay, then how much is I1?
1.1.
1.1 ampere. Okay, great. And then how much is I3?
0.9.
0. So this is 0.9 ampere. Okay, I think the time is over. This is already 5 o'clock. So I will stop here. But if you have any question, you can ask me. I shall stay. Otherwise, the class is over. You may leave. No problem.